Hi. So I'm going to be talking to you about futures today and hopefully convincing you that, or at least some of you, that there's maybe an alternate way to handling concurrent programming than what's commonly done. And this is joint work with my former advisor, Frank Pfenning at Carnegie Mellon University. So first, I'm going to briefly define some terms. I know that some of this can be controversial at times, especially what people call concurrency. For the purposes of this talk, I'm going to call a computation concurrent when multiple parts of it, and I'll usually call these threads or tasks, can be run independently. This is independent of whether it's actually being run at the same time or time switching or something like this. And of course, concurrent programs can always be, or can potentially be run in parallel, running multiple of these threads really at the same time, and this can improve performance in various ways, either just constant factors or also the asymptotic performance. Now, there are always some difficulties with concurrent programming. Concurrent programs are notoriously difficult to write and get correct, and also notoriously difficult to reason about, and introduces all sorts of new opportunities for bugs. There's this nice write-up about real-world concurrency bugs in Go that highlights really a huge number of different problems that come up specifically because of concurrency. So, in languages for concurrency, there's really one main common approach that I've seen, and I think probably this is something that most people will agree on. There's frequently a sequential language that gets started with, and then some concurrency primitive is added to that to enable working with concurrent programs despite the underlying language being sequential. And there are lots of different types of primitives that can be used, and these put some sort of restriction on what programs can be written, often with the goal of making it easier to work with, easier to reason about, and that sort of thing. So for instance, there are all of these threading libraries like pthreads that you might use in C, or libraries for fork join computation in functional languages, and also futures, which are the focus of this talk. So in case you're not familiar with them, I'm going to talk briefly about what futures are. For this talk, I'm going to be using this x left arrow p semicolon q sort of imperative style notation because I think that it's fairly illustrative of what's going on. So this construct is going to allocate a new memory cell, x, going to create a new thread that will run p, and run q on the current thread, the one that existed beforehand, and p on the newly spawned thread concurrently. The idea here is that this is going to run p, store its result into x, and make that available to q. In the language that we've developed for this, p will eventually write to x, but of course, you could imagine if we had recursion, p might be entitled to write to x but not actually get there necessarily. And q is entitled to read from x if it wants to. This might also get called in some contexts, p is providing a future and q is touching the future to read it. There are all sorts of terms for this. So one thing that's critical about futures as compared to some of these other methods is that q is allowed to depend on the result of p, and this enables something called pipelining, which we'll discuss a little bit in the future. So first, a simple example to just highlight what exactly the difference is between futures and some of these other systems. Everyone here has probably seen the map function many times because it seems to be the standard example to get used. So here's a usual functional implementation of map. And here, using sort of the same notation that I've been writing before, a more imperative style where we talk about the destination that results get stored into. So I'm going to focus on this recursive portion. We can say that we write the result of calling f on x to some location y. We write the result of mapping f over the tail of the list x's to a new location ys. And then finally, we write the cons of y and ys into the location d to return the mapped list. So if we do this sequentially, we just do this step one at a time. First, we evaluate fx, then map fx's, and then we finally write the cons cell into d. If instead these arrows are treated as futures, then we would start evaluating fx, we would start evaluating map fx, and then we would immediately write the cons cell yy's into d and return immediately. So this could start to be used even if the map hasn't completely finished yet. So now this gives a good example for pipelining, where we process data in a series of stages, one after another, potentially in parallel, although sometimes it's nice to think about pipelines in more of a sequential sense for reasoning. So for instance, if we wanted to map multiple functions in sequence over a list, we could compose the map function with itself. First map f over the list L, and then map g over the resulting list FL. And if we implement this using futures, it's possible for the second map of G over the list to begin doing work before the first map finishes. So we can gain some speed up there potentially. And also in more complex examples, which honestly I don't fully understand, but the algorithms people say that it works, it's possible for pipelining to not only improve constant factors, but also asymptotic complexity. So there's these algorithms for parallel merges of trees or treeps and various other data structures that gets some speed up from the product of the sizes, or the product of the log of the sizes of the data structures to the sum of the sizes, which is a pretty good gain. So as a final piece of background, futures are far from a new idea. I'm not by any means claiming to have invented futures. They originated in multi-Lisp in 1985, well before I was born. But they are a common thing that appears all over the place in commonly used languages in the real world. So C++ has this standard future construct. C# calls these task T. JavaScript sometimes calls these promises, sometimes async await, depending on who you talk to. So these are used all over the place. They have significant practical use cases. But the key problem that I see, at least, and what I'm hoping to address with this talk, is that the semantics of these are very ad hoc, especially in these cases. I mean, JavaScript semantics is rather non-existent. But even in languages that are trying to be more formal, the semantics of futures or of other concurrency primitives tends to be sort of tacked on to the base language of sequential programs. So in this talk, I'm going to focus on two contributions of the paper, the first of which is giving a logical foundation for futures, so tying these to a proofs as programs interpretation of a logic. And particularly, this will give us, incidentally, a first formalization of linear futures. And I also hope that I'll give some justification for what I call a concurrency first perspective for concurrent programming. And there's also a variety of other contributions that appear only in the paper. In general, this system that we developed, while it mostly works nicely with futures, we can also present lots of other mixed concurrent sequential programming approaches, and these are all interoperable, which is a nice feature. Okay, so to actually give the formalization of futures, we have a typing judgment that looks like this. We've got not just variables on the left-hand side, but also a variable on the right-hand side here that is the result or destination. So this Z is the location that we're storing the result to, and C here is going to be the type of the result data. And then this object P here is, of course, the program. And all of these variables on the left are thought of as addresses that the process P is allowed to read data from, and of course the types describe what that data looks like. I'll also briefly talk about what the state of a running program looks like in the system, and this is going to be some set of objects where we have threads. In thread AP, this represents a thread that's running the program P, and A is the destination where P is eventually going to store the result that it computes. And then we also have persistent memory cells represented with this bang prefix, and this is just going to be a memory cell that stores some data D at an address A. And for evaluation, we'll formalize this by some rules that replace a subset of the objects in the state of a program with a different set of objects. So multi-set or set rewriting rules, if you're familiar with the concept. And the typing rule for futures looks like this. We have our x left arrow p semicolon q construct, and we want to say that this eventually produces some z of type C. Well, q should produce that z of type C eventually, and we want to allow it to use x that P is going to produce, and over here we have just P produces this x of type A. Now, this is exactly the logical rule of cut from the sequent calculus. We'll look a little bit later at some of the other connections, but this is the main focus here. And the evaluation rule is quite simple for this. If we have a thread that's evaluating a future, this can simply take a step to two separate threads, one evaluating the left-hand side P and one evaluating the right-hand side Q. So we spawn this new thread to run P and continue running Q on the original thread. So briefly, we're working with a sequent calculus here. So we have left and right introduction rules. And broadly, the right rules are going to write to a future. The left rules are going to read from a future. And the identity or axiom rule is going to copy data from one location in memory to another or from one future to another. I don't really want to get into details for time reasons, though. But taken as a whole, when we have all of these together, this language with futures corresponds to a presentation of logic called the semi-axiomatic sequent calculus, which is from recent work by some of my collaborators and myself. And this is another facet of the correspondence between logic and programming. So just like we can get from natural deduction to the simply typed lambda calculus via interpreting proofs as programs, similarly, we get the same kind of relationship here, which is why I justify this as logically founded. So one note is that this definition is well behaved with a variety of logics. So it's most natural to start with structural intuitionistic logic, but we can replace that with something different to get a differently behaved type of future. So notably, if we use linear logic here, specifically intuitionistic linear logic, we get a system of linear futures, which have to be read from exactly once. And again, I'm not an algorithms expert, but I am told that linear futures can be used in some pipelining algorithms to get asymptotic performance improvements over regular futures, which is surprising, but means that there is potentially a very real use case for this. Okay, so now this language that I've presented so far, the only way that we can compose two programs is via futures. But creating new threads can have a lot of overhead, and many of the threads in this language are going to do very little work before terminating. Like maybe they'll write a single value or read something and then immediately write something else. So we don't necessarily want to spawn a new thread every time. As a simple solution to this, we can introduce a sequential composition or sequential cut operation, which will write much the same way as the futures, but with a little seek over the arrow. And the idea is that this should be typed exactly the same as the futures, but behave slightly differently when it runs. So this will still allocate x, but instead of running or spawning a new thread to run p, it will run p first on this existing thread, store its result in x, and then only run q once p has fully run to completion and stored its result in x. And other than that evaluation difference, this is identical to the concurrent cut using futures, but by writing some programs with this, we're able to manually choose where to create new threads or not and potentially improve efficiency. It's also potentially possible to automate this in some way, but it's not really something that we've looked into. Okay, so briefly some results. We have some system of typing for single processes. It's possible to also extend this to typing for running program states. So a running program state, again, was some collection of threads containing processes, as well as some collection of memory cells containing data. And we define a final state to be one that only contains cells. Everything has already finished writing. There are no more running threads. So once we do this, we can prove some of the standard sorts of results for a programming language. We can show progress, that a well-typed state is either final, so everything has written to a cell already, or there's a further step it can take. We can show a preservation result, that the type of a state is preserved by computation steps. And we also have a confluence result, that the order of steps in concurrently running threads is unimportant to the end result. So in conclusion, this gives a formalization of futures based on logic that comes very closely from this semi-axiomatic presentation of logic. And we naturally get futures as a result of this. So this suggests, at least to me, that a concurrency-first approach where we start with the concurrent portion of the language and then implement sequentiality or synchronization afterwards is a viable and potentially even better way to reason about concurrent programming, rather than starting with a sequential language and adding on some ad hoc concurrent features. And also by adjusting the underlying logic, we can get other forms of futures. Linear futures are the only ones that so far I know of a use case for, but there may well be benefits to, say, affine futures that I just haven't encountered yet. And then finally, we can implement sequentiality for this by just changing the evaluation order imposed by a scheduler, rather than having to have some fully separate sequence of sequential semantics. So all of this can be done in the same semantics, and then we just add a scheduling layer on top to decide what gets run sequentially and what gets run concurrently. And that gets us back to roughly the setting of a usual mixed sequential concurrent language. So there's a variety of possible future work, and some of this is also ongoing. Like, for instance, adding in recursion to the language and trying to prove termination with some sorts of restrictions, maybe only having inductive types. Trying to give a sense of program equivalence so that we can get to eventually having dependent types for this language, with the eventual goal being to have a concurrent type theory for reasoning about concurrent programs more broadly. So yeah, this says 22 out of 25 because I can't get the references to not be counted, but that's all I have for you right now. Thank you.